Thank you. Thank you for the introduction. So I'm Roman Rumpler, and I'm actually not the person most related to the work that I'm going to present tonight. I'm replacing my two colleagues who have been working on this project. And I'm from the MWL laboratory, so acoustics, working with acoustics. And this will be mainly the focus of the presentation tonight is about noise reduction and how to maximize noise reduction possibilities with poroelastic materials in our case. So noise, if we have a look at noise and the problems we still have with damping and noise in our societies, here is one talk that we can find from a TED presentation. So if I put that in a...
It's time to start designing for our ears. Architects and designers tend to focus exclusively on these. They use these to design with and they design for them, which is why we end up sitting in restaurants that look like this and sound like this, shouting from a foot away to try and be heard by our dinner companion. Or why we get on aeroplanes, which cost £200 million, with somebody talking through an old-fashioned telephone handset on a cheap stereo system, making us jump out of our skins. We're designing environments that make us crazy. And it's not just our quality of life which suffers. So
it's, I'll stop here, but just to say that acoustics, it can come down to a lot of areas in our life, and so we saw the transport industry, and we saw also architecture, so design of buildings. And one very useful tool, which one is PowerPoint? A very useful data we have for tool we have for noise reduction is the use of poroelastic materials. So what are these poroelastic materials? It's materials which are made of two types of materials. You have a frame, a structure usually, and then you have a liquid. And you have some interaction between this solid and this fluid, which have very nice properties in terms of acoustics, which can be used to reduce the noise in the environment we are in. So some examples of poroelastic materials, you can see them every day in every single aspect of your life. We have a lot of porous materials in the nature. We can see here from instance wood, bone is porous materials where you have bone and you have little inclusions of air in the bone. Honeycomb from bees working tool is also a poroelastic material. Now when we come closer and closer to what has been made by men, we have a lot of other tools. We come to industrial cases. We have porous materials which are completely designed in order to very specific for damping of sound, of acoustic waves. And it can be used in the aeronautical industry, in the car industry, and in the building industry. Now, what is existing today? Well, these poroelastic materials, if you look at them, of course, you can have very different properties if you take them in different directions. If we take the honeycomb from the bees, for instance, if you look at them only with the light, for instance, you can see that if you take in one direction, like it's taken in this picture, you can see the light through the holes. Now you turn it 90 degrees, and of course, you don't see anything anymore. And it's exactly the same with sound. So we have to use all these properties of these poroelastic materials that you can have in many directions. But that's the problem we have now. In the industry, we only consider one direction because it's easy to do. It's assumed that whatever the direction you're going to look at your material, it's going to behave the same. That's totally wrong for many materials. You can be completely off track with that. So for instance, for measurements, the measurements are done only in one direction. So what you assume, basically, is you take this material on the left, which has been manufactured in a way so that it reacts in this direction, this way, and another material, and you take two samples and you make a measurement, a characterization of the materials with an industrial process in only one direction, this direction, and of course you will have a completely different behavior of your materials. For acoustic purposes, that can be dramatic differences. So, of course, and that's a standard of measuring, so you can't accept that if you want to get to much refined solutions in terms of acoustics. So what my colleagues have been doing is they have been trying to work in all the directions of the materials so as to be able to play with these directions in order to further enhance the acoustic qualities of these materials. And they have come up with an experimental setup for that. Okay, so there's a norm. I'm not going to go into details, and of course we can go further into details, but there's a norm which, a standard which only measures in one direction. What they have done is they have come with a way to measure in 2 points, so you have an input and an output. Okay, so from 2 points you can get a measure, and then you can shift. You can see all this, in this cubic form, you have inputs and outputs on all the faces of the cube. So you can change the points of inputs and outputs as you wish on this cubic sample. So from that, mathematically speaking, you can collect all this data in a matrix, and you can get then information over the all the directions of the acoustic, the poroelastic material. So they have come up with this setup, as well as all the processing behind this setup in order to get the information in all the directions. And it has huge consequences for the industry, because of course, even though the standards are not yet there, if you want to get the best out of your material, of course, the industry partners are going to be very interested in such an approach. So they have come with this method, which has very important consequences in terms of performance and possibly business, if we can get into such a solution into an industrial application. We can see who it can benefit. It can benefit laboratories, it can benefit industries who produce poroelastic materials, but also the one who receives them and want to check on the quality of the poroelastic materials they have ordered. So that's the only drawback we would see right now with what they have come up with is the fact that now you need fairly large samples, 10 centimeters of size for this cubic material, which is not possible for all poroelastic materials we have at hand. So we would have to work on the smaller test measurement setup. So the possibilities, I briefly introduced them. While you're in lab, you could sell the information, send me your sample, and I can measure the properties, acoustic properties of your sample, and I can sell this service. Or another application has said both production and use of poroelastic materials for acoustic applications. Both types of industries could be interested, and of course, there are other possibilities that we might not be seeing at the moment on that. So this is very quick general information about what has come up, and of course I can try to answer most of your questions right now because I know a little bit about their work. I will be here this week, and they will be back from abroad at the end of the week, so my two colleagues, Christophe and Peter, can then be contacted, of course, for further requests on their project. Thank you very much, and please come up with your questions.